In the early mornings of 13th June 1944, the Nazi regime launched a new weapon on London. The first of the V1, as they were called, hit a railway bridge on Mile End in London, killing 6 people and rendering over 200 homeless. Over the course of next 9 months, an estimated 2,300 flying bombs hit London, killing an estimated 5,500 people. V1 was the first of operational cruise missiles capable of carrying an 850 kg warhead and could be operated from a distance of 250 kilometers at any time of the day or night. It was certainly a formidable weapon of terror. However, if this could be precision guided to hit the ammunition factories, it would become a strategic threat to the war. Was it really precision guided? How was the accuracy? This question was very, very critical to answer. Discovering the answer required to go through the bomb maps as well as looking at statistics textbook. R.D. Clark, a 31-year-old actuarian, found the answer to this question using a distribution called Poisson Distribution. He discovered that the bombs were not precision guided, but actually a cause of random chance, since the number of bombs per unit area was given by Poisson distribution. It exactly fitted the Poisson distribution. Hi, I am Sachin. I am the co-founder of AccelerateAI, and in today's video, we are going to talk about a special type of data called Poisson count data, in which we'll look at how Poisson distribution is used, as well as we'll cover modeling of such kind of a data using Poisson regression. So we'll talk about the premise of these count models and why and where do we encounter them. Then we'll look at specifically Poisson distribution and what it means. We'll cover how to model this using Poisson regression and interpret the coefficients. Also, Poisson distribution may not be applicable in certain cases, so we'll look at some of those challenges. And then to generalize those, we'll talk about negative binomial regression and zero inflated Poisson model, a very special case of this kind of a data set. We have talked about linear regression or ordinary least square regression, where our dependent variable is continuous and we use an equation of this particular form. If you want to refer to one of my previous videos, you can do so just to refresh your memory. Then we have also talked about variables which are binary or could be multi-category. And in such kind of variables, we cannot use a linear regression, but instead, to generalize it to a linear model, we use a link function called the logit function, or in case of multi-category, we use the softmax function. The probability of successes in this is given by this particular equation, which is called the sigmoid function. Now, how about count data? We often encounter this kind of a data set. Could we use a linear regression for this? Because ultimately what we are predicting are numbers and not categories. Well, what we are looking at here is small counts. And in such cases, we cannot use ordinary least square regression because the error terms here will not be normally distributed. So what do we do in such cases? Do we have a link function that can help us model this kind of a data? What is the equation for this? Answer to this is Poisson regression. Before I go to Poisson regression, let's talk about the Poisson distribution a little bit. Poisson distribution is used to model count data. So we often encounter count data in business situation. Here are some of the examples. The number of credit cards a person can hold, or the number of calls to a call center in a specific time window, let's say an hour, number of people ahead of you in a retail store checkout counter, and so on. So there are many, many cases where we encounter data which is always a whole number or count. This kind of a data is modeled using a standard distribution called the Poisson distribution, where the probability of observing a specific count, small y, is given by this particular formula, e to the power minus lambda into lambda to the power y divided by y factorial, where e is the Euler number. Lambda is the mean as well as the variance get observed in the population, and y could take any whole number like 1, 2, 3, and so on. So let's look at this as an example. Let's say our mean or lambda is 5. So this is the average number of counts that we see with repeated number of trials. The probability of observing 3 as a count would be given by this particular formula. So that probability turns out to be 0.14. Similarly, the probability of observing 5 in the count, 5 as a count, would be given by 0.175. So you get the idea of how we can calculate the probability for different counts. We could plot it for different values of lambda as well, and here is how the distribution will look like. As lambda increases, you can observe that the curve starts resembling a normal curve. But for smaller values of lambda, the curve is very, very different. And that is why for smaller counts, we need this special Poisson distribution to model it. So Poisson regression model, we assume that our target variable or the y variable counts. And these counts are always positive or 0. And they are whole numbers. The counts also follow a Poisson distribution. One of the very important assumptions of Poisson distribution is that the mean is equal to the variance. The explanatory variables could be any type of variables. They could be continuous, they could be binary or ordinal, and so on. These observations, however, should be independent of each other. To model the count-dependent variable, which we will assume follows a Poisson process, we'll get the parameters of these. How do we do that? So we have the expected value of count per period given by the formula, the conditional expected mean of y, conditional on xi, is given by lambda, which is exponential to the power xi or x dot beta if you write in matrix form. Now, taking log on both sides, we will see that log natural of the expected value will then become a linear function in x's. So we can assume that all of the betas, since these are independent, we can use a MLE or maximum likelihood estimation, taking the log likelihood on both sides. We get this kind of an equation. So ln of log will be given by this particular formula, minus e to the power xi beta plus yi xi beta minus ln of yi factorial. Solving for this using our sample data set, we'll get the values of the beta parameters. And then we can plug those in to get the expected count of for each of those values, 1, 2, 3, and so on. How do we interpret the coefficients? So once we estimated the coefficients, we will get the count by plugging in the values of betas and the values of the independent variables in this particular equation. Now this equation we know is also could be written by taking off the log on both sides, as the expected value will then become e to the power of beta naught plus beta 1 x1 and so on. Now, expanding this right hand side term will give us the expected value to be e times beta naught multiplied by e to the power beta 1 x1 and so on. So the interpretation of these coefficients is not additive, it is multiplicative impact in here. When x is interval scale, a unit increase in that particular variable x1 will change our expected count by a factor of e to the power beta 1. Also note that if beta 1 is positive, then y will increase with increasing value of x. However, if beta is negative, then y will decrease, or the count will decrease with increasing x. If x is a categorical variable, the we will follow the same rules as we do in ordinary least square regression, where we'll create dummy variables and one of them will be the base level. So the exponentiated coefficient will be the multiplicative term relative to the base level for that particular variable. So I hope this was all clear in terms of how to model this and how to interpret the coefficients, and then actually use this model to predict the average number of counts that you can observe, or the expected number of counts that could be observed. There are certain challenges with Poisson distribution. One of the important assumptions, as I mentioned, is that the mean has to be equal to the variance for a Poisson distribution. Now, we commonly encounter cases where our variance is greater than mean. This is called over dispersion. Under dispersion is rarely encountered. It's not that common. Another thing we observe is that the data could many times have more zeros than what would be estimated by the Poisson distribution. Consider some examples like this. So the number of insurance claims in a given population, we would see that a lot of people do not claim anything. Similarly, people who buy a subscription to a freemium product, majority of people would not buy, only a small percentage of people would opt to upgrade. Similarly, defects in a product, we would see that majority of the products will have 0 defects, whereas a few will have 1 or more than 1 defects. If you plot this frequency of distribution, we'll see a plot like this, where we will have a huge spike at the value of 0. This kind of a data set is called zero inflation, and we will not be able to predict this well using Poisson regression. So we need a special type of model for this, which we'll cover in the next few slides. So let's first talk about the over dispersion case and how do we solve for that, and then we'll look at the zero inflation cases. To compensate for over dispersion, we use a distribution called the negative binomial distribution. Negative binomial distribution is the probability distribution of the number of successes and failures in a sequence of independent trials before we observe a specific number of sequences. For example, consider 10 coin tosses, and in that we want to observe 3 successive heads. What would be the probability of observing 3 successive heads in a toss of 10 coins? This kind of a distribution would be called a negative binomial distribution. Some of the key points of a negative binomial experiment are that we have X number of repeated trials. Each of the trials has 2 possible outcomes. One is termed as a success, the other is termed as a failure. The probability of success in each trial is the same. In our case of coin trial, it is 0.5. If it's a biased coin, that probability could change. The output of one trial is independent of the output of other trial in a binomial experiment. And the experiment is carried out until we observe a specific number of successes. So the negative binomial distribution probability is computed using this particular formula. It's given by x minus 1 choose r minus 1 into the probability of success raised to the power r into 1 minus p raised to the power x minus r. 1 minus p would be the probability of failure. If we plot this particular curve, this is how it looks like, given by the green line here. So as we can see, the negative binomial distribution is over dispersed than the Poisson distribution, which is given by the red curve here for comparison purposes. The green, red, dark green is where they both overlap. So for negative binomial distribution, we have 2 terms, the mean as well as the variance, which helps us control how the variance is there in the data set. So negative binomial regression is a generalization of this Poisson regression. It loosens the assumption that variance is equal to mean. Here again, we will have the equation as the expected or conditional value of y will be equal to e to the power of beta naught plus beta 1 x1 and so on. However, the probability distribution is assumed to be a negative binomial distribution, and then we'll solve for the parameters using maximum likelihood estimation as we do in all other cases. Here is an example of a problem in genetics where the data is highly dispersed, and as you can see, Poisson distribution doesn't do a very good well, especially when the mean gene expression level increases. And negative binomial regression does fit the distribution very, very well. So there are cases where in order to generalize the Poisson regression, we use the negative binomial regression. There's another case, the zero inflated Poisson regression or ZIP model as they are specifically called. This is useful for analyzing this kind of a data set where we have a highly skewed sequence of counts with a large proportion of zeros, as I had said earlier. So consider an example where an investor or a trader, there could be two types of them. Those who sometimes just did not trade versus there would be investors who never trade. Similarly, people who did not claim an insurance in a particular period versus those who did not buy insurance at all. So these kind of people will skew the data on the number of insurance claims that we'll get. To model for this, the ZIP models are also called a two-part model or a mixture model, and it allows for two different processes. One drives whether the value is a zero or a non-zero, and the other one will drive the values which are strictly positive counts. This kind of a model was first proposed by a person named Diane Lambert, who is a statistician. She got her PhD from University of Rochester and then worked in Carnegie Mellon University as a faculty for a very, very long time. Currently, she works for Google. So in ZIP or zero inflated Poisson regression, the structure is that it has two kinds of zeros, true zeros and excess zeros. And we employ two model components. One of them governs the binary distribution of these excess zeros, right? So in our case here, these are the excess zeros which are not explained by the Poisson regression. And these are the true zeros. They would be zeros even if we apply Poisson distribution. So the first model we use, which is a logic model typically, which says whether the zero falls in this particular area, whether it's an excess zero or it's a true zero. And the second process is governed by the Poisson distribution, which will generate the count of the values. And some of those could be true zeros as well. So here, the formulation looks like that. The probability of y equal to 0 will be given by an additional parameter pi plus 1 minus pi times e to the power minus lambda, where pi is the probability of those extra zeros observed. Lambda, as usual, is the expected Poisson count. And the probability for y equal to yi, where yi could be 1, 2, 3, and so on, will be given by 1 minus pi times lambda to the power yi e to the power minus lambda by yi factorial. So this, as you can observe, is our standard Poisson regression. However, this is an extra term that is multiplied here for zero inflation. The mean of zero inflation regression is 1 minus pi times lambda, and the variance is lambda times 1 minus pi into 1 plus pi times lambda. Here again, the mean and variance are different. Now, we can apply this and then solve for the parameters pi and lambda. And once we get that values, we could plug in those into the equation to get the expected count for different values of x. In zero inflated Poisson regression, we get two different intercepts. The first intercept has the usual interpretation that this is the expected number of count when all of the independent variables are 0. There is also another intercept, typically called the 0 b0 intercept. And what this means is the odds of observing extra zeros. So these are our extra zeros given by here. converting that odds to probability, we can get it as odds divided by odds plus 1, which as an example comes out to be, let's say, 30%. So 30% is the probability of these extra zeros being observed in the entire data set. So I hope this interpretation is something that you will be able to remember. So that's all about the theory about Poisson regression, negative binomial regression, and a special case as zero inflated Poisson regression. In Python, we could create models for all of these using the stats models package. There we have regression with discrete dependent variables. So it provides us an API for Poisson regression, one for negative binomial, and a zero inflated Poisson regression as well. Plugging in the data sets will give us all of the parameters. There are also a lot of other different regression models that could be used for discrete dependent variables. With this, I come to an end to this session. If you found this helpful, do subscribe to our channel on YouTube, and I'll also highly recommend all of you to join the conversation on LinkedIn at AccelerateAI. Thank you so much for watching.